I'm sure that you are here for what he's going to talk about. And also I got really interested when I heard the title of his talk. He's going to answer the question, when do I get my intelligent robot? Sven is an expert in the field of neural networks. He did his PhD in computer science, and today he works for the University of Hamburg. I'm really curious when we will all get our own robots. Thank you for being here, Sven Magg.
Thank you very much. Yeah, thank you for coming. And maybe I have to disappoint you. As Rudy already said, he gave up on his robot. And I will actually take my 12 minutes to tell you that it might be quite some time until you actually really get an intelligent robot. I'm not talking about Roombas who can maybe not hit the wall to turn around. I'm talking about a more general one we know from the movies. So why do I think this? I have 11 minutes to convince you. I'm from the field of neural networks. We work with neural networks. Nowadays, deep neural networks, everybody has heard this term, I'm pretty sure. Yeah, it's the term that drives AI in the last 10 years. And when neural networks started, it started already with the idea of a robot in mind. So they said, I want to build something intelligent. How do I do this? Let's look at something intelligent. Let's look at us. And in us, it's actually the brain who does the thinking, who is the intelligent bit. So what people thought at the time, 80 years ago already, that, well, to build an intelligent robot, I just have to look at the brain. I model the brain a little bit mathematically, and then I just take the parts that make me intelligent and move that over to a robot. Done. 80 years ago, the first neural models came up, mathematic models. And now, 80 years later, we are actually in the deep neural age. Deep neural networks are around for 10 years now, and everybody has seen something from a deep neural network. Everybody has a phone, uses speech recognition, all deep neural networks behind. So it seems that we already have intelligence, or at least many people think so. The networks that we use nowadays are quite optimized for computers, highly abstract mathematical models, deep because many layers of neurons that information has to flow through, and they're quite far away from the biological inspiration. We still claim we are bio-inspired and work with bio-inspired models, but if we are honest, it's very far away from the biological cousin in our heads. But the interesting thing and what drove AI the last 10 years was how we learn, or how our brain actually gets intelligence and learns. And the thing is, we learn from data, and that's the whole thing that changed in AI 10, 15 years ago. We went from pre-programming things to actually things that learn automatically by just throwing data at them in masses. So how does it work? We see objects as children. Say, I see a tomato, I see lots of tomatoes. And over time, I can actually distinguish a tomato from the rest of my environment. I know what a tomato is, and I have a concept tomato in my head. I do this year after year, and maybe not after years, but suddenly I can also distinguish bananas from tomatoes. I know what a banana or what distinguishes a banana from a tomato. Maybe the color, maybe the shape. And I saw lots of them. So I learned to distinguish objects in the easiest case. And I do that with everything. Objects, sounds, everything we see. I always try to take the data and try to see how to distinguish that data from other data. So I classify it. That's all our brain does, or mostly, a simplification. And the same thing we did with neural networks. So we throw data at them. I give them a few million images of objects, and the robot can do the same. Actually better than us at the end. So quite often, for most of the tasks we use deep neural networks, they actually end up doing the task that we train them for better. This is good if we think about a robot, right? Maybe bad for us. Rudy might lose his job soon. But did we actually achieve intelligence? We call it AI. And we work with robots and other systems. I just try to show you a few. We have our Nico robot here that we always try, a small humanoid robot. And, well, the robot can look into this world, can look at faces, and can actually see faces, recognize emotion in a face. So it can talk to me, recognizing my emotion and reacting to it. It can use sound. So here it tries to find out what's in these small Kinder eggs. We put different stuff inside, like sand, salt, and so on. And it just used the sound of it. And it could learn to distinguish up to 40 objects with quite a good accuracy, much better than I could do it. Like he could distinguish between salt and sand in an egg. It can also learn to move. So we started it from scratch. It has a neural network driving the motors, and it had to learn to grasp objects like a child. It works. It just grasps an object, put it somewhere else, grasps it again, and repeats this overnight, maybe 2 days. And at the end, he can grasp the object almost anywhere in his field, quite accurately. And it works. We also can put it together. So here, the robot just got told, pick up the carrots. You can't hear it. But then the robot had to identify the carrot here, so object recognition, and then used its learned grasping module to actually grasp the object. And you can just see the camera shake a little bit when the student jumped up because he was so happy that it worked. So all this is state of the art now. So this is what we do now. And you can say, well, that's not far away from the intelligent robot that helps him in the house, does the dishes, makes my breakfast. But I claim it's far away because we use the wrong methods. All the deep neural learning hype that's currently going on is great to do single tasks. But this is not a single task. A robot doesn't do one single task. It does a lot of tasks in parallel. So what we actually do, or what our brain does all the time, we get lots of different modalities as input. We hear sound constantly vision, constantly sound. I feel my environment, I feel myself, I know where my motors are at any given time. And the brain incorporates that all together into one concept, tomato. I can see the tomato, hear the squishy noises, feel the tomato, and that all is an experience to me. For me, it's not a class tomato. I don't see an object and say, yeah, that's tomato, and I know it can be a little bit different. I immediately know how it tastes, I immediately know how it feels. I know how to grasp it so that it doesn't break. If we do the same with a robot, we give them all the input at the same time, as we've seen in the last video, it works. But what we had to do is, every single task was a single network. So we had a network doing the object detection, we had a network doing the sound, speech recognition, we had a network doing the haptic stuff and the movement, and all networks worked in parallel. They all worked, so maybe a small error comes up, the speech understands tornado instead of tomato, but I can solve this, I can do a voting in the end, and I end up with an intelligent robot. But it's not efficient, doesn't scale at all. Now imagine you have 100 tasks, 100 networks, each of them needed one computer. So that doesn't scale very fast. Or doesn't scale at all after a short while. So what did we do wrong? Where did we go wrong? And it's that single task training. So we train a neural network for one given task until it's a perfect network, or almost as perfect as we can do. But this somehow is wrong. Our brain does something different. What our brain actually does it has interconnections between these networks. So when I learn about a tomato, I immediately touch the tomato. I bite into the tomato as a child. I play around with the tomato. And all of those experiences together actually form that concept. The brain regions influence each other all the time. If I hear the word walking, my motor brain lights up. So somehow my speech part asks the motor part, what the hell is walking? Can you explain walking to me? So there are interconnections in the brain. And this we're completely missing here. Those networks don't talk to each other. And it's actually not that easy to make them talk to each other, because the concepts they learn are so vastly different to each other that it's difficult to actually get them together. And this is what we are currently working on, or where we have to work on to get intelligent machines. People usually say immediately, more data. That's a typical deep neural network approach. If it doesn't work well, more data. We can generate data for many tasks, but not all of them. Some tasks are just incredibly difficult to get data for. Dialogues. I can listen to lots of people, but how to cover all possible dialogues for a network to learn? Somebody has to annotate that, has to go through and actually correct all the errors. How can I do this? Doesn't work. Also doesn't scale. For single tasks, automated driving works well. I can drive around with a car for half a year, collect data, train a network to recognize everything I saw in that half a year. And I will still miss some parts. First example there was, well, data was collected in Germany and then was used in Sweden. Snow was a lot more common there suddenly. So the network just wasn't trained to deal with snowy landscapes, and it actually didn't recognize much of it. So what can we do? We call it cross-modal learning. That's exactly the idea. From the start, I have one network or several networks, but they learn together. They correct each other from the beginning. I see an image of a tomato, I hear the word tomato, and I immediately start connecting these two things, trying to learn a shared representation, not only single representations per network. Transfer learning is a thing. If I've learned already a task, maybe playing chess, currently Alpha 0 beats you anytime at any board game, if you train it for. But if I trained it for chess, I have to completely start fresh if I want to play Go. It can't learn both games at the same time. It could, but then the third game, it wouldn't know again. But transfer learning is the idea that we have a network that is trained for something and we can transfer that data already over to a different task. Best example, our emotion recognition. If I know how to recognize faces, I learn a lot about faces and how they are different. Why not start with that network and then start learning emotions as well? Maybe 80% of the knowledge that I need to detect emotions or differentiate emotions is already there in this other network. I just don't know where. But maybe I can move that information over or start already not at zero. One of the most important parts about robotics, and that's where Rudy and I think, go different directions. In virtual reality, I can simulate everything. I can do that pretty well. We actually interact with our environment. We also simulate that, but we simulate it in a real world with all the noise I have there, with all the errors that can happen. That's something I have to learn. A robot has to learn that sometimes its actions don't work. Sometimes my motor fails a little bit and I don't end up at that position where I plan to. I can learn that. We actually know how to react to this. We don't learn perfect positioning. We actually move close and then we look at it and then we do the small adjustments at the end just by looking at it and correcting ourselves. If I now have to grab something behind me, which I've definitely seen a few minutes ago, I wouldn't be able to actually get there correctly. Because our brain doesn't work like this. Active exploration and learning. Last thing, and we have to explain it. We have to know why a network did something. So this is not robotics, general AI, but if you're interested, look at our webpage. We have lots of robot videos. Ask questions.
Is this working? Yeah. I'm actually really impressed by this really nice and very clear explanation. Also, thank you much for these nice slides. I really loved your talk, and I'm sure you also did. And I'm really interested in your questions. What came up to your mind when you just listened to the really sad story that we will not...
Nobody will get a robot.
Get an intelligent robot. Yes?
I was wondering if it's an attempt to have AIs actually simply imitate humans and have just the observation of humans as a data source and just really... And if they are just really told to imitate what they do, is that a thing?
Well, no. That was what we did in the past. We actually looked at how humans do it and then tried to copy that exactly over. Neural networks learn from the data, so it depends on the data. If I give them exactly the same data as I think so, it will do the same errors that I do when seeing the same data. So it learns from that data. There's a good example from America. People tried to train a neural network how to detect a criminal. They gave faces from all criminals currently in the jail to the neural network. What did the network say? If you're black, you're a criminal. Why? Because, well, 80% of the jail inmates are black in America. Is that because they're criminal or because humans made some biased decisions? So the network can only learn the bias. So in the end, yes, they will learn what we give them. Master has used before, apparently, and they called it a creative move in that moment, just because they didn't know it. But that network learned something that wasn't trained from a human and couldn't have been trained by a human.
I just had a question in mind when you were talking. I mean, we train neural networks by giving data, And that's how the neural networks train themselves, let's say that way. And so far you've mentioned that we could like see the tomato, we can hear it, or we could whatever. But why can't we feed neural networks with the combination of the different senses? I mean, we have only 5 senses. It's not like there is a like limitless amount of senses we have. So for me, it feels like it should also be possible to train it with the combination of all of them. And then you might get to a result which is closer to what you've just called an intelligent robot.
Well, the problem is that the network then learns differently. It still gets all data at the same time. Let's say a tomato feel and a tomato look. But what it then learns is if those always appear together, it learns that they have to appear together. So it won't learn to identify a tomato by image only if the feel is missing. So our networks do that all independently. We have a network only for the haptic, but they talk to each other and they teach each other very quickly. That's the difference. We can already feed our robots all the data at the same time, but it's then limited. Then what if new data comes in? It still doesn't learn well, and it's a quite complex network. It actually doesn't learn if there's too much data at once. So the method we currently use is just the wrong method. In the end, we have to present all the data at the same time, and it should learn like we do.
Okay, so you're saying that if there is another method coming up, there might be my intelligent robot in the next...
Yes, we are working on it. I mean, we are actively working on all these concepts, but there we are at the beginning. Deep neural network goes a different direction to get optimized. This is a different direction to the current deep learning.
I think you were first.
This is probably a bit special question, but I always see like you have neural networks that can that don't have to be trained. They can train themselves. They can like segment different stuff, put it in groups and whatever. And we always talk here by labeling data, saying, okay, this is a tomato, and you see a picture, and there's a tomato. And if you go back into like learning theory, you have something like Kubernetics, where you more or less train the system how to learn, how to get new information out of certain data or whatever. Do you see any new interesting ideas how to combine more or less this Kubernetic approach to machine learning?
It's already used. Clustering algorithms do exactly this. And there are networks that do exactly this, learning unsupervised. No training data on the top that I train towards. The problem is I don't get very far. I can work with raw data and separate that out, see what's in the data. The problem is also our brain does that, but at one point it stops and it takes over with feedback signals that come from our cortex. So even in the beginning, the first layers in my visual system already are influenced by expectation. If I hear a lion roaring, I turn around and my brain already is prepared to detect lions faster than other things. These feedback signals we can't use yet. We haven't figured out how yet. And without those, I actually don't get the necessary training signals to do higher level things. So for lower level, that works pretty well. We use that already in combination with deep neural networks. But you don't get very far without training signals at one point. So yeah. Jure.
As a question, we are really sure that this kind of really fantastic mathematic neural networks are really the answer to the question, what is intelligence? So this goes too far, but are we really on the way to achieve really artificial intelligence with them?
I don't know whether we achieve, when we achieve already intelligent behavior, that we can see, but our level of intelligence, I can always say, well, we are only built by neurons. So if we really can achieve this, the problem is complexity. We have a few billion neurons and a few trillion connections. It's far away from our models still. We couldn't compute this. But maybe it's just the size and the combination of many smaller networks that actually can get us to the same behavior. And if I behave the same as you, am I then intelligent as a robot? That was a good last word.
Yes,
Man.
That was a perfect last, like a perfect ending. I'm sure you really enjoyed it. We want to thank you with a bottle of wine again. Maybe if you also struggle about the idea that the totally intelligent robot might not come up in the next year, maybe the bottle of wine helps you over it. Yeah.